Okay, so you would have heard about, probably Jamie would have said something about an operational amplifier, or op amps. So today what we're going to do very quickly is we're going to explain what an amplifier is, because that puts us in the context of what an operational amplifier is. They're two different things. We'll be able to identify and explain the terminals, the purposes and the terminals of an op amp, which you guys may have come across in the pre-quiz. We'll be able to explain how an op amp behaves really basically with and without a key piece of behavior called negative feedback. Pretty much, well, most of the work we will do is with operational amplifiers in this negative feedback configuration. And we'll figure out what that is shortly. And when the op amp is in negative feedback, there are some really basic behaviors and characteristics of the op amp when it's in negative feedback, and you must understand what those are, because if you understand, there's only a couple of rules, but once you understand those rules, everything becomes a lot easier. Okay, so firstly, what's an amplifier? So who tinkers with their car audio? Anybody? Yep. So you've tinkered with car audio, you know what an amplifier is. It takes in a small, in your case, audio signal, and it cranks out big doof beats, right, basically. Yeah. So pretty much any information, whether that's audio signals, speech signals, video signals, they all can be encoded in the electrical domain as electrical signals, or really fluctuations in voltage. So so you guys, who's done lab 1 already? Who's yet to, so you have played with a signal generator, and then you see that in the signal generator you can generate voltages with, like, say, a sine wave, for instance, and that sine wave at different frequencies, which you fiddled around with. You made really annoying sounds with the piezo. When you change that frequency, you get different sounds. Well, all speech signals are really rapid fluctuations in voltages translated into speakers. So pretty much any signal can be encoded into some kind of electrical current or voltage. So what an amplifier does, it takes these small signals and turns them into much bigger signals. And why is this useful? Well, it turns out that if I want to get some information from, say, down here up to the back to you guys, I could turn off the mic, for instance, but then what happens is that the signal gets smaller and smaller as it reaches you guys in the back. All right, and that's what tends to happen here. Signals tend to drop with distance. But what we can do is we can use the microphone system, and we can take the signal from my voice, turn it into an electrical signal via the microphone here, and then we can transmit that electrical signal up to the speakers, which are located all around the room, and that has amplified my voice. And these are all done via amplifiers. Okay? Now, this is probably the most tangible application that we can come across, but amplifiers pretty much exist everywhere. So these video signals that come from my laptop all the way to the projector, all the way to the screen, those signals would have had to be amplified from my laptop all the way through to the projector to be projected on here. Otherwise, we would be losing a lot of video quality. So that's the main reason we use amplifiers. What are some types of amplifiers? So for any audiophiles out there, there are some things called vacuum tube amplifiers. And these tubes have really low pressure, and if at best they take all of the air out of there. When you take air out of somewhere, there's no molecules through here, so any electrons that go through and get shot through the vacuum tube don't encounter any noise. So these are really good low noise amplifiers. Transistors. You may or may not have come across transistors in the past. We don't touch on them much in this course. But these are some really basic types of amplifiers. MOSFETs are another type of transistor. And over here, this guy is what we're talking about today. These are called operational amplifiers. And this is exactly what one looks like. I think it might be the actual one you have. Yes, it's the TL074CN. TL074. And all it is, it's a computer microchip which has a number of pins that you can slot into your breadboard. So if you've had your lab already, you know what that looks like. And if you haven't, well, you soon will. Okay, so let's zoom in on the op amp. So as I said, in our course, you'll be using this op amp, the TL074. And why is this little chip great? And why do we teach you about it? It's because it's really, really versatile, and you can get it to do a lot of things just from this one microchip integrated circuit package. So what you can actually do is you can take signals and you can do all of these different functions on them. You can multiply signals together. You can amplify signals. So this, when we're talking about amplification, that's only one thing it can do. All right? It's just amplification, which is multiplying signals. You can also divide signals, add and subtract signals. You can do calculus with this operational amplifier. You can integrate and differentiate signals. You can construct what's called a filter. So remember in the first lecture, Jamie said, oh, what's this circuit do? And it had two operational amplifiers on it, and it was actually a filter. You can compare signals. So you can say, is one signal bigger than another? And you can even create what we call a clock signal for digital applications. And we'll learn about digital applications in week 5. Okay, so so that's an op amp in real life that you guys get to work with. Now, how do we represent an op amp in our circuit diagrams? And this is the symbol for the operational amplifier. So it's a triangle with 5 terminals. Okay, so you've got these little things here. They're all terminals. Okay, this one, this one, this one, this one, and this one. And importantly, there is a plus and a minus symbol on these 2 terminals over here. Now, these plus and minus symbols are very important. They represent distinct pins. So they represent distinct pins on our actual op amp. Okay? And if you mix them up when you're wiring it together, then your op amp will do different things than what you expected. Okay, so these 2 terminals here are called, respectively, the non-inverting terminal. So if there's a plus, that means that the input terminal, this non-inverting terminal, is usually known as V plus or in plus. So in plus is in the book. V plus is also a common reference for that. The negative sign signifies what we call the inverting terminal. Why is it inverting? We'll find out soon. Okay, so that's the difference between those 2. Over here, we have an output terminal. So the way we're viewing this is we've got a couple of inputs coming on from the left, and on the right-hand side, we have an output. Now, the output voltage can be calculated relative to the 2 input voltages on the terminals V plus and V minus, and that can be done via this equation. Okay? V out equals AOL times V plus subtract V minus. Now you notice that this V plus minus V minus is the difference in voltage between these 2 terminals. AOL here is called the open loop gain. I will be referring to that from time to time. So if you do see this symbol, you go, oh, what's that? Well, it's the open loop gain. And usually this is a fairly large number. Okay, so this might be the order of 10,000 or so. Usually. It varies between op amps. So just as a quick thought process, if V plus is, say, 1 volt and V minus is, say, 0 volts, then the difference between here would be 1 volt, and we would get some multiplication by AOL, which could be about 10,000. So what would be the output on V out in that case? 10,000 volts. Now, does that make sense? Does that make sense in terms of the laws of physics? You put in a really small voltage and then suddenly you get 10,000 volts out. That would be really awesome because we could generate a whole load of electricity for putting in really small amounts of electricity. Okay, so physically that doesn't quite make sense, and the reason is because, like any electronic component, this op amp requires power. Okay, and that's what these two terminals are. Okay, these two terminals are called the supply terminals, and these are signified via these abbreviations, VCC or VS plus or VEE and VS minus. So the top one is usually the positive supply, the bottom one is usually the negative supply. So what do these two things do? Well, what we do is we connect up, as the name suggests, a supply voltage, and this might be, say, 5 volts, for instance, up here, and this might be negative 5 volts. What does that do? Well, the output of this op amp can only ever be as large as the supply terminal, okay? So I'm supplying this microchip with 5 volts. Well, the maximum output of our op amp can only be 5 volts, regardless of what this equation outputs. Okay, so we don't get 10,000 volts. We only get a maximum of 5 volts out if the supply voltages are 5 and negative 5. Okay, so we're not violating any law of conservation of energy here. We're not generating free energy, unfortunately. So this is a very, very important point because we need to understand that any electronics needs power, and we can't output more power than is supplied by the circuit. Okay. If you probably don't have it here, there's no lab today, so you probably don't have it here, but if you look at your op amp chip, this is how you determine which pins correspond to what parts of the amplifier. Okay, so on every chip there will be a little thing called a little dimple on one end of the chip, and the pin directly to the left of the dimple, as you have the dimple oriented upwards, is always pin 1. That's for pretty much all integrated circuits or chips that you buy. That's a standard. Okay, and then if you then turn to the back of your lab book, there will be a little diagram, and that will tell you exactly what terminal of an op amp each of these pins corresponds to. So over here, pin 1 corresponds to output 1 on your chip. And you count around the chip, and you can figure out exactly what terminals correspond to which pins on your leg. Note that in this TL074 that you guys have, there are 4 operational amplifiers in there. Okay? So you've got, for each op amp, you've got 3 terminals. You've got the plus and the minus and the output. They're all in plus, in minus, and the output. And over here, you've got 2, which is the VS minus and the VS plus. Okay, so you put in your supply voltages into these 2, and that means that for this particular chip, they all have a common supply voltage. So it might be 10 volts, might be 5 volts, whatever you're using for your circuitry. Okay, so what's actually inside the op amp? Okay, so for that little triangle, if we broke that apart and had a look inside, you would see this. Well, the circuit diagram would look like this. Your reaction may be the same as the cat's. And what's inside this op amp is actually a number of different components, which are all created in silicon and then all broken off and packaged up into that nice little package that you get in your lab kit. And inside that little package, you get about 15 transistors, 12 resistors. You might have you have a capacitor and a diode in there, for instance. So those are these things over here. And this whole circuit is quite complex to understand. So a lot of people, by the end of their electrical engineering degree, still don't understand how it works properly. I mean, if you go into that area, obviously you will. But electrical engineering is such a large area that you may get away with just using this thing and not having to worry about the insides. And that's quite common in most areas of engineering. You work with systems, you connect systems together. You don't necessarily have to create each individual system. So we're not going to ask you in this course anything to do with what's in here. So don't worry. We just use it as a black box, if you will. So we draw a box around it. We say everything inside is something. There's just some terminals on the outside. And we just expect you to understand how the outside behavior works. Okay, so all of those transistors and resistors can be basically simplified into this model. This is called the simple op amp model. And as you can see, as the name suggests, it is a lot simpler than the model that we saw before. Okay, so last time I saw you, we learnt about these things. So this is a, what is it? A voltage source or current source? Voltage, and is it dependent or independent? It's a dependent voltage source, okay? And it's dependent on another voltage, okay? And you can start seeing why we needed to teach you that, because this AOL is really the scaling factor, and this V plus minus V minus is really the voltage that is controlling the output voltage on this source. So here's V plus, subtract V minus. Okay, so that's really what the voltage is across here. Let's get rid of that. Okay, so that's V plus minus V minus across here. So we assume that everything is relative to a 0 volts, which is usually the voltage directly between the two supply voltages. Okay, so if you have a supply voltage of 5 volts up here and a negative supply voltage here of -5, then we assume 0 volts is the midpoint between those two. So this is one really good example of how you can simplify one really enormously complex circuit into a really simple model which has two resistors. So this is R out and this is R in, and one voltage source. And that's basically what we have here. Input resistance, output resistance, and the voltage source. Okay, so we can even take that one step further. So that's the simple op amp model. We can take it one step further and even turn that into what we call the ideal op amp model. So in the ideal case, these resistances, Ri and Ro and AOL, they have certain values that we can assume if the op amp is ideal, and that is that the input resistance is infinity, the output resistance is 0, and the AOL scaling factor is infinity. Now, why are we doing all this? The reason we're doing all this is that at the level that we are using the op amp in ENG1030, we don't need to have calculations that are entirely accurate when we are doing circuit analysis with these op amps. It's really just good enough that we use what we call this ideal op amp model. And we don't want to be using anything that we don't need to be if it complicates things. Okay? So this is really handy because if I substitute those values into the op amp model, I just get this instead. Okay, and what is this? Well, we now have an infinite resistance between V plus and V minus. So basically, the circuit looks like, well, these two terminals are floating and there's no current going through the terminals. And on the output, we have V out is equal to infinity times V plus minus V minus. So really, if V plus is greater than V minus, the output will be really large and positive, and hence the output will go exactly to what the two supply voltages are. So if you had Vs. So if V plus is greater than V minus, then the output will be Vs plus. And if V minus is greater than V plus, the output will be Vs minus. Okay, so here is the first implication of this ideal op amp model. And if it's in yellow and it's big, bold red writing, it's important. Okay, The important thing here is that because these are open circuits, there's nothing connected here, nothing connected here. No current goes in or out of these terminals. Okay? This is the first golden rule of op amps. The current I plus going into or out of this positive input terminal and this current I minus going into or out of this negative input terminal is 0. No current goes into or out of there. And we'll harp on that time and time again, and I'll show you how that makes life really easy when we are designing circuits using these op amps. Okay, so this means that all we need to worry about is the voltages at the input terminals, and we will get a certain voltage at the output terminal, which will, in this case, depend on which one is bigger. If V plus is bigger or V minus is bigger, and that the output will go all the way up or all the way down to the supply voltages. Okay, so remember, this is a big number, so even a small difference here will make all of this really large, but the output can only go as large as Vs plus, or it can only go as negative as Vs minus. Okay, so this is what I've described here multiple times is called clipping. Okay, so op amps exhibit this behavior called clipping. So if the voltage on the output, can only ever be between the supply voltages. Okay, so if you want larger output from your op amp, you need to supply it with a larger voltage on the supply terminals. Okay, and whenever the voltage hits the supply terminals, it's called clipping. All right. So let's take a quick breather. Let's have a look at this melts question. So it's a good time to have a break because we've been talking for about half an hour. Okay, so assuming the ideal op amp case that we've just talked about, can you work out what the voltage is, what V out is in this case on this model? And I'll open up the question. So that's this one. And I'll make sure it's unlocked. Good. Okay. So remember, so I've thrown a whole load of stuff at you there about the input voltages. How do you calculate the output voltage, and what is the maximum value that the output voltage can be? So put that all together, and if you understand what's going on, well, even if you don't understand, have a go, and we can see, hopefully we can clear up exactly how this op amp is behaving. So give you a couple of minutes, have a breather as well. Talk to your neighbors if you don't understand. Even if you do understand, check that your neighbor thinks you're correct. Okay, so just in case, because it's not on the slide and you don't have the notes, remember what the output equation is? It's AOL times V plus minus V minus. And remember that this number is usually really big. Okay, so of the order of 10,000 or 100,000. All right. and that the output can only be ever as large as the supply voltages. All right, we good? I think that's pretty much it, everybody. All right, so let's have a look. Okay, so here's what it looks like. So what have we got? So we've got a majority of people saying it's D, -5 volts. A minority of people saying it's 5 volts, and we're getting really small. 9 out of 115 takes -2 and 2 volts. Previously, I did see that this was pretty equal for the 5 volts and -5 volts. Okay, so the actual correct answer is, in fact, D. It's -5 volts. Now, the reason that this is the case, okay, so over here, you've got 0 volts on V plus. Okay, and we've got 2 volts on V minus, and on the output we will have AOL, so AOL times V plus minus V minus, so this could be something big, let's say 10,000, it doesn't really matter, times V plus, which is 0 volts, subtract 2 volts. So if we evaluate this, we get -2 volts, and this is 10,000. Okay, so it's important to realize that this AOL is a scaling factor that multiplies the output of this calculation. So you've got over here -20,000 volts. And as we've been saying, it's not possible for the op amp to supply a voltage larger than or smaller than the supply rails. So because this is -20,000 volts, the voltage can only ever go as negative as the negative supply voltage. So that's why this is -5 volts. If these two terminals were swapped around, so if this was 2 volts up here and this was 0 volts, then the answer would be 5 volts because this negative sign would be positive, because you'd have 2 volts minus 0 volts times 10,000. Okay? So hopefully that clears it up a little bit. If it doesn't, then please feel free to come and get me to talk through it again or explain it in a little bit more detail. But it's good that a lot of us are following this. It's actually quite tricky stuff to throw at you in this first lecture. A lot of other courses, even when I did it back in undergrad, didn't do it in first year. I did it in second year. So we think that you guys are smarter than I was. So that's why you guys are doing it now. Okay? Okay, so far we're saying, how's an op amp work? Well, now let's get into like how we would actually use it. Okay, so from what I've been explaining so far is that the op amp's behavior gives you an output which is basically going to be clipped depending on the difference between these two voltages. So if V plus is greater than V minus, then the output basically goes to the top supply voltage, Vs plus. If it's the other way around, so if V plus was 0 and V minus were 2, then the voltage goes all the way down to negative supply rail. Okay, so let's say I were to plot two values of V plus and V minus. So over here on the green line, let's say this is the value of V plus, and it follows this green line which is ramping up from this value all the way to this value and then ramping back down to this value with respect to time. And I plotted V minus, which is just, let's say it's a steady voltage at whatever this value is, and it just continues on across here. Well, if those two values of voltage were connected to the op amp, then what would happen? Well, the output voltage, which I've put in red, would, in this case over here, be just the minus supply voltage, because over here, V minus is bigger than V plus. When we get to this point, the output voltage of the op amp would swing to the positive supply voltage, because now in this region, in this region, V plus is greater than V minus. So over here, V minus is greater than V plus. And then over here in this region, again, V plus, why does it do that? V plus is greater than, V minus is greater than V plus. So if we use the op amp in this way, it's what we call a comparator, and that's a really useful circuit because it allows the op amp to tell you whenever a voltage has exceeded some sort of reference voltage. So basically it's saying, well, here's my reference voltage at V minus. Whenever a voltage that I attach to the positive terminal is bigger than V minus, give me an output, which is over here, Vs plus. Otherwise, the output should stay low at Vs minus. And I say high and low because this leads us into digital systems in a couple of weeks. Okay, hooray, this is great. But this still doesn't look like what we're talking about when I introduced amplifiers. Okay, so it's still not taking a small signal and turning it into a big signal. All right, so now I'm going to introduce the most important way that we use the op amp, and that's called negative feedback. Okay, it's not when we grade your exams and give you a poor mark. That's not the kind of negative feedback we're talking about. The negative feedback we're talking about is a condition where I attach the output terminal back into the negative input terminal. Okay, so in this circuit, there is a path between the output terminal and the negative input terminal. And when this occurs, this is called negative feedback. Now, in this case, the path is actually just a single wire in this particular diagram, but that's not the only case. In this path, you could have resistors. That would still constitute a negative feedback path. You could have capacitors. Okay, that's the symbol for a capacitor. And that would still be a negative feedback path. So anytime current can flow from the output terminal here all the way back to the negative input terminal, and that's really important, it has to be the negative input terminal. This is called negative feedback. Okay, so remember that, because if you see an op amp which is in negative feedback, you can do some really useful things in terms of calculations. Okay, so in this case, I won't go through this part exhaustively, but in your own time, when you want to understand what is happening, some of you may want to, and some of you may just want to know that when this is connected, something happens. Well, if you go through this bit of logic, at this point, the main thing that happens when you have negative feedback is that V positive is equal to V minus, and in this case, it's also equal to V out and Vs. Okay, so here's the main thing. When I connect V out back to V minus via a path, the main thing that happens here is that this happens. V plus is equal to V minus, okay? And if you don't remember anything else, you need to remember this. When there is negative feedback, this condition exists. V plus will be equal to V minus. And this is explained intuitively via this 6-step process. You don't need to particularly remember that. You just need to remember this condition here. Okay? So, we won't go too much into that. We're going to finish up pretty much here. So only in this negative feedback condition, okay, the op amp will try to make these two voltages equal. Okay, V plus equal to V minus. And how does it do this? Well, remember that diagram where we had all those transistors? This diagram here. Since I've got a little bit of time, I can show you the diagram. So for the diagram here, next one. So in this diagram, all these transistors and resistors and this capacitor and this diode, when this output voltage, when this output terminal is connected back into the negative terminal, this sets off a whole load of chain reactions within this circuit. And what the whole circuit basically does is it tries to adjust the voltages such that V plus is equal to V minus. Okay, so that's an enormously complex process. Inside the operational amplifier, it'll adjust its voltages on the transistors, it'll adjust the currents going through the transistors, all in the process to make these two voltages, V plus equals V minus. That's the key thing you want to understand. Yep.
The voltage output be zero then?
In this case, you mean the one that I'm showing?
Yeah.
Yep, so if I go over here, the voltage output here is, now here's the thing. So the voltage output here is connected to V minus, and over here Vs is not zero. Okay, so we're assuming that this Vs is some value Vs. Now, I'm not saying that this is actually zero. I'm saying that the difference is really, really small. So V plus minus V minus is really, really small. And when it's multiplied by that AOL, so remember this V out is equal to AOL times this difference. Well, this difference isn't exactly zero. It's really small. And when they multiply together, the whole op amp sets up these two voltages so that they're essentially the same, but not exactly the same. Okay? So in the ideal case, and because we only care in the ideal case for all of our calculations, we can assume that this is true. In reality, it's not quite true, but in the ideal case for our purposes, this condition holds. And along with what we saw before with this ideal op amp assumption, so for our ideal op amp, we had V plus and V minus going into our op amp, V out. No current goes in and out of this, right? So these two things I will leave you with today as the things you need to remember for the rest of the stuff we do with op amps. And they're called the golden rules of the op amps, okay? So take some time to understand this lecture, because the next 5 lectures after this will rely on basically making use of these two rules, okay? Okay, cool. So we finished a little bit early. Thank you. And this is the summary slide of what we talked about.